Hello children, in the previous sessions we discussed about electrical energy and electrical power. In this session we are going to discuss about what is electromotive force and what is the terminal voltage and how electromotive force and terminal voltage are related to the internal energy. Children, in order to understand the EMF and the terminal voltage, once we need to recall how electric cell is made. Children, two conductors of suitable materials are placed in an appropriate electrolyte taken in a vessel. So, this is how actually an electric cell is made. Means in order to make electric cell, we need a vessel, appropriate electrolyte, and in that we have to place two conductors of suitable material. But children, so what is the duty actually, what is the purpose of this electric cell, dear children? We know that it maintains a constant potential difference. It's very important. Cell always maintains constant potential difference between the terminals, between these two terminals, by a chemical change in order to obtain a continuous flow of charges, between these two terminals, which means what? It is maintaining constant potential difference. So, dear children, that potential difference between these two terminals only we can call it as a EMF, that is electromotive force. Children, what is electromotive force? The potential difference between the terminals of the cell, but in an open circuit is called electromotive force. Children, as I am saying that it is in open circuit, do you think that some current is drawn? No, current is not drawn. So, when no current is drawn, so there will be some potential difference between the terminals of the cell. I mean what? We are talking about a new cell which is not connected in the circuit and it is ready to do the work. Is called actually EMF. So children, as I said that it is ready to do the work actually. For what it will do the work actually? In order to make the charges to flow around the circuit. It will do some work. So, now we will discuss on which factors does the EMF depends. It is very important, children. So, on which factor it depends, that is EMF, and on which factor it does not depend, also very important. Let us see. First one, the material and depends on the nature of the electrolyte used. Children, it is very important. EMF depends on the material of the electrodes and it also depends on the nature of the electrolyte. But dear children, do you think that it depends on the shape and size of the electrodes? No, it is not that. Children, look at here. So, very important thing is that it does not depend on distance between the electrodes. So, there are the factors on which it depends and there are the factors which does not depend. So, once again let us recall what is EMF. When no current is drawn, the potential difference between the terminals of the cell, that is in an open circuit, strictly we are talking about open circuit only. So, the potential difference between the terminals of the cell in an open circuit is called EMF. Then dear children, what happens when you connect, this cell in a circuit? For example, here is, it is a bulb. Let us say here is switch. Now it is an open circuit only. The moment when you turn on the switch, then what will happen, dear children? Definitely in external circuit, there will be a flow of charges. So that the bulb will be glowing. It is very clear. The bulb will be glowing. Means what here? Electric cell started doing work in order to make the charges to move in an entire circuit. But teacher, now in this position, don't you think that some amount of energy is consumed by the bulb? Obviously, it is consumed by the bulb. Now it is a closed circuit. In this case, teacher, in a closed circuit, if you can measure the potential difference between the terminals of the cell, obviously we will find little bit less value when we compare with the open circuit. So, the potential difference between the terminals of the cell in a closed circuit is called terminal voltage. So, it is very important. I repeat once again, what is the terminal voltage? The potential difference between the terminals of the cell in a closed circuit is called terminal voltage. Even the terminal voltage also, dear children, is nothing but the work done to make the charges to move in only external circuit. Children, try to understand what is EMF. It is a work done to move the charges in an entire circuit, but whereas terminal voltage is what? The amount of work done to move the charges only in an external circuit. Children, how EMF and terminal voltage are related? It's also very important. Let us see once again. Children, here epsilon is a letter which is used to represent the EMF, and here V is a letter which is used to represent the terminal voltage. Now let us see how EMF and terminal voltage are related. So in an open circuit, EMF and terminal voltage are equal, whereas in a closed circuit, EMF is greater than the terminal voltage, whereas in a during charging here, EMF is less than that of the terminal voltage. Now children, we'll try to understand the relation between electromotive force, terminal voltage and potential drop. Children, look at here. For suppose here at anode, let us say example only, at anode, one unit positive charge is there. So this has to be sent. Of course, what is like current agent? Of course, there again we'll be having two types of current. Don't get confused. So we will assume it's a flow of positive charge. Also, we will assume that will take as a conventional, like a direction of conventional current. But actually, the electrons are flowing opposite to the direction. Electrons are will be flowing opposite to the direction. So dear children, so here let assume one positive charge is there. So in order to make this positive charge to move this in this circuit, children, it is external circuit. So here some work has to be done. Children, try to understand. Let us discuss in the symbols. So let us represent this cell in the symbols. Actually, how can we make? So this is positive and a negative, dear children. So here the charge is, let us say here the charge is there. Let us say it's a unit positive charge is there here. So in order to make this charge, dear children, to move, in order to make this charge to move in external circuit, let us say some work has to be done, right? Some work has to be done. So strictly in an external circuit only we are talking. Means what here? To move this charge from A to C only. So let us say that work done is WAC. Let us represent AC. So what is WAC here? What does it represent? It represents the work done to move that positive charge from A to C. But circuit has to be completed, then only there will be a current in the circuit. That we know very well. Means whatever the charge which has brought till cathode, let us say, it has to be moved from again cathode to anode. Means what? Inside of cell, children. So far we spoke about actually in external circuit. Now we are talking about inside of the cell. So in order to move the charge inside of cell, some work has to be done. From where to where? From C to A. So let us represent that as a WCA. Children, try to understand. WAC is what actually? The amount of work done to move from A to C, that is in external circuit. Whereas what is WCA? The amount of work done to move the charge within the cell, that is from C to A. That is C to A. But dear children, then how can we calculate the total work done? Of course, by adding these two. Then we will get a total work done in order to move the charge in entire circuit, that is A to A. Let us say it is A to C. So that's very easy to us to understand. C to A. Children, try to understand. So what is WA to A? It is the work done to move a charge in entire circuit from A to A. Then here what is WA to C? The amount of work done to move the charge from A to C. That is only in external circuit. What is WCA? The amount of work done to move the charge within the cell. That is from C to A. So mathematically, when you can add these two works, definitely we will get the total work done. But dear children, one reading WA to A, WA to C, WC to A, it is not that much comfortable. So let us give some symbols to this, dear children. So WA to A, let us represent with a capital W only. Whereas WA to C, let us represent with a W dash. But whereas WCA, let us represent with a small w. It's a small w. Now on both sides, let us try to divide with a charge Q. So this will be Q. So So children, look at here. So it is a work done per charge only. It is also work done per charge only. So all are work done only in order to move the charge only. But what is the difference, dear children? Difference in the amount of work done are different. So in this first case, dear children, so it is a amount of work done to move the charge in an entire circuit is called EMF. It's very so children, it is called actually EMF. Let us represent with epsilon. Children, this amount of work done to move a charge in entire circuit is called EMF. Then what is this, dear children? The amount of work done to move the charge in an external circuit is called terminal voltage. Then what is this here? The amount of work done to move the charge within the cell is called potential drop. So here mathematically if you can see, EMF is equal to the sum of the terminal voltage and potential drop. Here we will get a one doubt. Here, why are we calling it as a potential drop? Dear children, whatever the work is done, to move the charge from C to A, there is no use actually. Means there some amount of work is done to overcome the resistance offered by the electrolyte. Now we will discuss about actually internal resistance. Children, so the word itself will give you a clue to understand what actually internal resistance. Internal, which means what? Talking about what? Inside of that cell. Inside of that cell, what will be there? Electrolyte will be there. So already we discussed what is the EMF, dear children? What is EMF? The amount of work done to move the charge, that unit positive charge, in an entire circuit, which means what? In external as well as what? Internal also. Means what? The charge has to be moved through the electrolyte also. So here what happens is that here, of course, electrolyte might be the best conductor, no doubt about it. But dear children, still it offers some resistance. That resistance only we can call it as a internal resistance, which means what? The resistance offered by the electrolyte to the flow of charges is called internal resistance. We will represent with a small r. But dear children, in a symbols, when we are making a circuit, how can we represent actually internal resistance? Because it is inside, we cannot see, we cannot show like how will show like a symbols like ammeter, okay, battery symbol we can. But how can we show the internal resistance when we are making the circuit? Let us see, dear children. So here, whenever you make, for example, circuit, let us say it is a battery. But where that internal resistance is a matter of actually what? Inside of that cell actually. But how? Here only, beside only, we will make a symbol of resistor like this. Means just you have to think that, children, this is inside. Again I am saying you here, there is no any resistor like this connected to the battery and we are calling it internal resistance. It is not that. So this what actually inside. So as we cannot show inside, it is too difficult to show inside of that battery. So just for sake of our convenience, to understand in a better way, we are showing just in a beside only. So this will be what actually internal resistance. Now we will see on which factors does the internal resistance depend. Dear children, internal resistance depends on the size. It's very important. It is a size of the electrodes. Why depends on the size of the electrode? Size means what? I am talking about surface area. That is capital A. I am talking about capital. That is surface area. Capital A. Dear children, if the surface area is more, then what will happen here? More charges are collected. As more charges are collected means what? In external circuit, there will be a more flow of current. As there is a more flow of current, which means what? Resistance will be the less. So here we can say that here internal resistance is inversely proportional to the surface area. And the second point, children, it depends on the distance between the electrodes, the small d. Dear children, the between two what we can say conductors, that is cathode and anode, if distance is more, that is one case. Another case, distance is less. Dear children, in which case charges will reach the what we can say cathode and anode very easily when the distance is less. When distance is more means what, dear children? The length of that what electrolyte between the anode and a cathode is increasing. Already we discussed, dear children, when the distance, that is the length increases, obviously what will happen? The resistance increases. Why? There are more chances of collision. So as the number of collisions increases, due to which what will happen? There won't be any proper flow of charges. So there will be a more resistance. So which means what? As the distance between the electrodes increases, dear children, what happened? The internal resistance also increases. So first point, R is inversely proportional to A, and here R is proportional to D. And third factor is very, very important. This is the concentration of the electrolyte here. Electrolyte. So dear children, if you can take electrolyte with more concentration, then what will happen? Obviously, the internal resistance also increases. Means more will be the concentration of the electrolyte, more will be the internal resistance. And the fourth factor is that temperature. So here, as the temperature of the electrolyte increases, what happens? The internal resistance decreases, so that there will be a more flow of charges. So here, internal resistance is inversely proportional to the temperature. So dear children, these are the factors on which internal resistance depends. Let us recall, what is internal resistance? The resistance offered by the electrolyte to the flow of charges is called internal resistance, and internal resistance depends on the surface area of the electrodes, distance between the electrodes, and the concentration of the electrolyte and the temperature of the electrolyte. But dear children, how to calculate internal resistance and how is it related to the terminal voltage and EMF is very, very important. Dear children, when this circuit is connected, for example, it is completed, let us say. So here is a battery, already it is there, and here some resistors are there. Let us say it's one more resistor. Here two resistors are there like this, okay, and it has completed like this. Just imagine. So dear children, when the switch is on, what will happen? Current starts flowing. Current starts flowing. Try to understand. So let us say it is R1 resistor and it is R2. Children, don't get confused here. R1, R2 are external resistors. Whereas here small r is what? Internal resistance. But here how to calculate terminal voltage and how to calculate potential drop are very, very important. Children, it's very much important. So simple, teacher. Let us say here capital I is a total current which is flowing in the circuit. Then how to calculate potential drop? Children, potential drop, as I said, that will represent with a small v. So here potential drop. So how to calculate potential drop means total current into internal resistance. Children, I repeat once here. If you can multiply total current with internal resistance, you will get actually potential drop. Then how to calculate the terminal voltage, that is capital VD, children. Children, don't get confused. Capital V is a terminal voltage. So this we can total current into, here thing is that, children, we should not consider the internal resistance. Only we have to consider the external resistance only. Then you make it a one doubt. Why we should not consider the internal resistance? Children, what is terminal voltage? Let us recall. It is the amount of work done to move that unit positive charge in an external circuit only. So as the work is done to move the charge in external circuit, we will consider the only external resistance in order to calculate the terminal voltage. It is very important. Now look at here, in this example, children, two resistors are connected. So means what? We have to calculate the resultant resistance. As these two are connected in a parallel, children, the resultant resistance will be Rp. Resultant resistance will be Rp. Means what? The parallel combination, and we will calculate Rp value here. So here V is equal to I into Rp. Children, don't get confused here. So what is potential drop? How to calculate? Potential drop is the amount of work done to move the charge within the cell. As it is a work done to move the charge within the cell, we are considering the internal resistance. What is the potential drop? It is the amount of work done to move the charge in external circuit. That's what we are considering the external resistance. Very important. So it is small v is equal to I into small r, internal resistance, and a capital V is equal to total current into external, total resistance only, but it is a external resistance. Now let us try to make a relation between small v and capital V. Dear children, so every time writing RP, it's may not be comfortable. So directly what we'll do, capital R only we will take. So this, children, you should understand, capital R means what? It is a external circuit. Might be 10 resistors, 100 resistors are connected. We will take the resultant resistance of that resistor which are connected externally only. Let it be, it is the equation 1 and here is equation 2. So children, can we write like this from equation 1, dear children? Can we write here internal resistance is equal to potential drop by current? Yes, we can write. We can write. And whereas from equation 2, can we write like this? I is equal to V by R? Yes, we can write. And just we discussed the, we derived the expression which gives a relation between EMF, potential drop and terminal voltage. Is what, dear children? EMF is equal to terminal voltage plus potential drop. So from this, potential drop is equal to, we can write EMF minus V. So this potential drop is equal to EMF minus V. Let us substitute in this here. So write on here, we are going to substitute. So we will get here small r is equal to small v value we will take from here. So that is minus V, okay, by, it is by, and I is equal to what can we write? We can write I is equal to V by R, it is. I is equal to V by R. That is, we can write it is a V by R only. Now teacher, it's a denominator and denominator will be the numerator. So it will be R into epsilon minus V by, what we can say, capital V. Children, this V is a common LCM for these both terms. So let us write separately. So then we will get is equal to R into here epsilon by V minus it is V by V. So here, dear children, V gets cancelled. So what is left here? Small r is equal to capital R into epsilon by V minus 1. So dear children, this is how actually internal resistance, that is small v, and EMF and terminal voltage are related. So very important, this expression we use to do some numericals. Okay, copy it. Dear children, in next session we will be solving the numericals based on series combination, parallel combination, and even the expression which we obtained, that is a relation between internal resistance, EMF and terminal voltage. Thank you so much. All the very best.